Hello and welcome to the CAINE Forensics video series. In this video, we will look at using the Wireshark packet analyzer to capture and analyze network traffic. Please help me out by hitting the subscribe button so I can spend less time down the rabbit hole. Wireshark is a network protocol analyzer used for network analysis, troubleshooting, education, and development. From a forensic standpoint, we can use Wireshark to collect network traffic so we can tell what devices are communicating with each other. This analysis may lead us to devices that we are interested in or devices which don't belong on the network. The program can do live capture and offline analysis. Live data can be read from the Ethernet, Wi-Fi, Bluetooth, or other interfaces. For this video, we will focus on using Wireshark to analyze basic network protocols. Wireshark runs on Windows, Mac OS, and Linux. It is free and can be downloaded from wireshark.org. I will be using the CAINE distro where Wireshark already comes pre-installed to make things easier. So let's go ahead and launch Wireshark. One thing to note is that although we can see it in the menu under Forensic Tools, Network Forensics, Wireshark, if you launch it this way, you will not see the interfaces that we will need to access to do the capture. So what we are going to do is launch a terminal window, and then from the terminal window type sudo Wireshark. We first see this setup page where we can enter capture filters and select the interface to capture. On my machine, I see a number of interfaces ranging from the Ethernet, which is named ENP0S31F6, to the loopback interface, to the Wi-Fi, which is named WLP2S0, and even Bluetooth. I have this laptop connected to the network via the Ethernet port, so let's choose that. We will generate some traffic along with the other machines that is on the network. And then we can stop the capture by clicking on the red square. Let's take a look at the user interface. We first have the menu items up on top, ranging from File, Edit, View, etc. And then we have the quick access icons right underneath. So the blue shark fin is to start a capture, the red square is to stop, green shark fin is to restart another capture, etc. Then we have the packet list section where it lists each captured packet. The next section is the packet details where it displays the details of the packet selected from the packet list. And any selected details will be displayed in the packet's byte section in hexadecimal. Lastly, we have the status bar on the very bottom where it gives you information about either the PCAP file being written to or the selection of the hex data that's being hovered over in the packet byte section. Let's take a look at some basic network protocols and what their associated data packets look like on the network. The first one we're going to look at is the ARP address resolution protocol, which is used to associate a MAC address with an IP address. From a packet standpoint, we see the ARP request in the packet list section on top, and once we highlight it, we will see the details in the packet details pane in the middle. Here in the details view, the packet gets categorized into the layered OSI model. The first line is layer 1, the physical layer, where information like the interface where the data was captured from, time information, frame number, frame length, etc. are listed. Notice that when the frame is selected in the details panel, all of the data in the bytes section is highlighted as the frame consists of all the bytes. The next line is layer 2, the data link layer, and in our case it's called the Ethernet. If we expand this line by clicking on the triangle and click on the individual components like the destination address, source address, or the type, You can see the byte section has the individual components highlighted. The next and last line is layer 3, the internet layer. In our case, it's the ARP protocol. If we click on this line of the packet, the byte section highlights the information related to the ARP protocol. If we expand this line and click on the individual components, like the hardware type, the protocol type, etc., you can see the byte section, which has the individual components highlighted. And if we go back to the list panel and select the next ARP packet, we can see the ARP response packet coming back from the destination computer. In the details pane, we can see the target MAC address and IP address being returned. A common network command is the ping command, which tests whether one machine can reach another machine. The way that ping works is that it sends an ICMP echo request to the target host and waits for the ICMP echo reply. In this capture, we can see in the packet list where machine 101 sends a ping echo request to machine 100 using the ICMP protocol. The next packet we see is the echo reply from machine 100 back to machine 101. For more details, we can look at the details view where we see lines from the physical layer and the entire frame. We see a breakdown for the data link layer under Ethernet 2. We see a breakdown for the network layer with the Internet Protocol version 4. And lastly, we see a line for the ICMP packet where you can do a deeper dive if you are a true packet head. Another common protocol you may encounter is the HTTP-related packets. This is when someone is surfing the internet and is using their browser to look at a website. If you are looking at the packet list, you will see a ton of traffic related to each session and also tons of traffic that belongs to other requests. One way to narrow down your focus is to follow a specific HTTP stream. Select the packet, right-click to get to the menu, then click Follow, and then HTTP Stream. Once you do this, you will get a pop-up window that contains all the traffic for that particular HTTP stream from both the requester and the website. You can further filter this down by selecting to look only at traffic from one side or the other. So here, I am selecting the traffic from the requester, which is in red, and we see that the requester sent a GET request for the page named bluemonkeyforensics.html to the server at IP of 192.168.10.102. Then I can select to only see the traffic returning from the website, which is in blue. And we can see here the HTML code for the web page containing the return to the requester. From a frame analysis standpoint, here I am clicking on the entire frame in the details pane, which you can see highlights everything in the bytes pane. Then I highlight the Ethernet 2 line of the data link layer, and I see that only the source and destination MAC addresses are highlighted in the bytes frame. Next, I highlight the Internet Protocol line of the Internet layer, and I see that the source and destination IPs for the entire frame are highlighted in the bytes panel. Next line selected is the Transmission Control Protocol, or TCP, of the transport layer. And this contains information about the source and destination ports, sequence number, etc. And lastly, the last line is the HTTP protocol. And here we can see the GET request sent and responded to. In this next capture, we are going to look at the TCP stream for the exact request, but using the HTTPS protocol instead of the HTTP protocol. When we follow the stream, we can see that the data is now encrypted on both ends as we expected. On the packet list, we can see that the TLS, Transport Layer Security, version 1.3 protocol was used instead of the HTTP protocol to send and receive data. Wireshark comes with certain color schemes denoting different types of captured protocols. The default colorings are pale orange for ARP packets, pink for ICMP packets, light blue for UDP packets, not colored with gray letters for broadcast packets, pale green for TCP packets, gray for TCP SYN and FIN transactions, red with orange letters to denote TCP resets. If you want to change the colors, look under the View and then Coloring Rules. And a pop-up panel will appear allowing you to change these colors. Let's talk about filters. If you just straightforward monitor your network, you could have thousands of packets going by every second. And it might be a little overwhelming in terms of the amount of data that you have to sift through. So in order to remove some packets from the display which are not relevant to your analysis, you can use certain expressions to narrow down the results. So those expressions include having a field name that you want to filter by, and then some relation, which is something like is equal to or not equal to, greater than, less than, contains, matches, etc. And then you can have that relation to a value, right? So it could be a text value of an IP number or some other number for a time value, or even a string for the name of the website, or just a certain string that you are looking for. So let's look at an example. So we can filter by protocol. So let's say we are only interested in the ARP, address resolution protocol. We can type in this filter bar here, ARP, A-R-P. And then once we hit return, the only thing that we get displayed are the ARP packets. Similarly, if we say we are not interested in the ICMP packets, we can type exclamation mark ICMP, and this will show you everything except for the ICMP packets. We can filter by other fields like the IP address field. So we can type ip.adder equals equals. And then let's say 192.168.10.102. That's my server IP. And so the results will give us only packets where the source or destination is that IP number. So in this particular case, what we're going to see is the HTTP traffic to and from that IP 102. We can filter by other things like a HTTP request protocol. Okay, so if we type in just http.request, this filter will only give us the requests for HTTP data, in which case we only have one request. Similarly, we can do the response. So we can do http.response, and that will give us the only response from that request. Another thing we can do is we can follow a TCP stream. So if we type in tcp.stream equals 0, this is only going to display to us the packets involved within what Wireshark determines to be stream numbers 0. So in this case, it was the request. It was the HTTP request for this particular page, bluemonkeyforensics.html. And we can change it to another stream. Let's say we look at tcp.stream equals 1. Now we're only seeing everything from stream 1, which in this case is the HTTPS request for bluemonkeyforensics.html. And if we go ahead and follow the stream, we can confirm that the data is all encrypted because we use the HTTPS protocol. We could add some compound filters by adding these Boolean connectives. So double ampersand for and, double pipe symbol for or. So we can say tcp.port equals 80, or tcp.port == 443. So what this is going to do is it is going to only give us traffic to port 80 and port 443, which is the HTTP and HTTPS traffic. All right, so that brings us to the end of this video, where we took a look at using Wireshark to capture data packets from a basic network setup. This could be very useful when you're facing an unfamiliar network where you need to perform forensic acquisitions. Hope you enjoyed it, and if so, click on the thumbs up icon to like this video. Please hit the subscribe button to get notified when the next video comes out. Also, please leave me messages in the comment section below so I know what you liked and didn't like, or what you may want to see in future videos. See you next time.